So far, all of our solver runs resulted in a unique optimal solution, okay, where exactly one corner of the simplex or feasible region, one corner, okay, will maximize or minimize our objective function. Some of the other special cases involve alternative or multiple optimal solutions, unbounded solutions, and infeasibility or no solutions at all. Alternative optimal solutions are encountered when multiple vertices, say 2 for simplicity, have the same value of the objective function, which means that all the points in between are optimal solutions as well. We discuss this in some more detail on the next slide. Unbounded solutions are encountered when we can increase or decrease the objective function while satisfying all the constraints indefinitely. The graphic in the top right corner shows that we can keep moving from either point A or B, all right, along respective rays, staying feasible in the green region, and continuing to increase the objective function indefinitely. Infeasibility is the direct opposite of the unboundedness. That is, instead of an open, endless green feasible region like this one here, there is no region at all. So no feasible, much less optimal solution exists. Both of these situations are most often encountered due to misspecification errors. For example, when less than or equal to is accidentally switched to greater than or equal to in one or more constraints. Sometimes, though, it can make business sense. There could be simply no way to have enough labor and material to produce a minimum number of products required. That is relatively easy to imagine in our example, right? If I find any one of these slides from the base model, okay, if instead x1 is greater than or equal to 0, essentially, right, x2 is greater than or equal to 0, we have, for example, x1 greater than 4, so x1 starts here, goes up, and x2 greater than or equal to 5, which is not even on the chart. You can imagine that this problem would not, the original problem, would be infeasible. Okay. Now we're going to switch to the alternative optima sheet in Excel, and we'll notice that we increased the marginal profit from $3 for drug 2 to 4. Okay, from $3 to 4. So what that in essence did, all right, it made our profit contours more, or profit lines more shallower than before. In other words, it was tilted sort of upwards towards the bottom. And specifically in this example, what it did, it's easier maybe to look at the chart on the slide, it made the material constraint, the red one here, overlap with the optimal profit contour of $12, as you'll see in a second. These are suboptimal at 10 and 8. Okay, so starting with vertex 0.0 or 0, I should say, the simplex method will simply move up to 0.3 and stop declaring it an optimal solution. So to see that, go back to Excel. Notice that we start with 0.0. I'll go to Premium Solver and simply run it. And notice that it moves up to 0.3 for the optimal profit of 12. I might have, increased a couple of decimals here so you can see the details, right? You can see you are on the material line, right, as we've been before, and you have 3 surplus hours of labor. However, if you type 1.2, 2.4, our original unique optimal solution from the base model, you'll notice that that one is obviously also on the material constraint and on the labor constraint that is at the intersection of the two, but it yields exactly $12 in profit as well. So that is an alternative to optimal solution. So is any point or any production schedule in between, again, looking at the chart here, in between the two. For example, let's see what I got. I got 1, okay, 1, and this is 2.5. Okay, I got 1, 2.5 with $12 in profit as well. All right, notice that this point is sort of closer to the original optimal solution 1.2, 2.4, right, which is still an alternative optimum, right? But now it's using a half an hour less labor. Okay, another point that I found, where is it? 0.5 pounds of drug 1 and 2.75 of drug 2. Okay, notice it's also just like the previous one on the material constraint. Same profit, $12, right? So that point would be about here. That's 275. Okay, but it uses even less labor. All right, it uses 10 and a quarter hours of labor. And finally, if you keep sliding towards top left, you end up, of course, at 0.3 that uses the least labor. So in that sense, between all these possible alternative optimum, in this simple example, it's probably the most preferable because it has used up the least amount of labor. Although the profit, again, notice remains exactly the same at $12. Okay, let's switch back to the presentation and pause.